Everything in our scientific intuition says the world is what it looks like. And the whole point of quantum mechanics is that we look in the world and what we see is something a little bit different than what the world really is. Quantum mechanics is central to modern technology, about the relationships between humans and computers, artificial intelligence, consciousness, minds. It is the way the world works. We're trying to do this just because we want to understand the fundamental nature of reality.
Are you optimistic that we will find a positive and amicable relationship with our technology, or are there dangers?
There's absolutely dangers. There always are. If you imagine that there is a percentage probability that a new technology will literally wipe out all of humanity, what percentage is acceptable? We're changing things rapidly, and you can point to specific things like climate change or nuclear weapons or bioweapons or whatever, but just the fact that we do have these amazing capacities and are rushing pell-mell to put them to use without thinking them through, that's bad. There's no reason to think we can't figure things out, and putting the effort in and recognizing, standing up, facing up to the puzzles that reality presents us with is part of what makes us human and part of what really makes life fun.
The world is changing. Inspiration is everywhere. It has never been so easy to connect, share, and bring people together. We're learning from others and finding the best in ourselves. Challenging our beliefs, sharing our vulnerability, overcoming our fears, transforming ourselves so we can transform the world. How far can we go?
This is London Real. I am Brian Rose. My guest today is...
How did the universe begin? Are we living in a simulation, and will AI take over the world? Well, these are some of the questions that I sat down and talked with Sean Carroll about. He's a physicist at Caltech, where my dad actually went to school, but he spent time training at Harvard and even at MIT, where I studied. And he's here to tell you that quantum mechanics is actually really relevant to you and your life. And I'm always impressed that so many people around the world really want to understand a lot about physics, about cosmology. And Sean is one of the best in the business. He's appeared on the Colbert Report, the History Channel, on the Rogan Experience 3 times. And he really has a great way of showing how this stuff applies to your life. And it's interesting to me how a physics professor from Caltech is more about philosophy, because this stuff affects the way that you and I live today. Quantum mechanics is all around us, and you are gonna love this episode. It taught me a lot about my own life, about the future, and how we all relate to each other. So sit back and enjoy this incredible episode with Sean Carroll. This is London Real. I am Brian Rose. My guest today is Sean Carroll, the American theoretical physicist specializing in quantum mechanics, gravity, and cosmology. Your research explores dark matter, extra dimensions, and the origins of the universe, and your work has been published in the New York Times and New Scientist magazine. You've also made television appearances on History Channel's The Universe, Morgan Freeman's Through the Wormhole, and the Colbert Report. Your latest book, Something Deeply Hidden, has been described by the physicist Brian Cox as an exploration of what it means to exist on this speck of dust in a possibly infinite universe. Sean, welcome to London Real.
Thanks very much for having me.
Great having you here. First of all, what's it like being in London? What does this city mean to you? How is it different than LA, where you're at now? You went to school in Boston. Like, what's the vibe when you land here?
I really enjoy London, for a lot of reasons. Like the cheesiest reason is just that it's a foreign country where they speak English. And as an American, of course, English is the only thing that I speak. So it's a wonderful way to get a different set of experiences. But I just love the charm, the culture, the history. Every little street corner has something going on.
And you're already exploring that. I know you bought like an umbrella. You're heading up to Edinburgh. I mean, you really get into the culture, don't you?
Going to be going to Cambridge, giving the Darwin lectures named after Charles Darwin. So just like everywhere you go, there's resonances of things that happened historically. And
science history here as well. Do you feel that when you're here? Like, wow, some big things happened here.
Tonight I'm giving a talk at the Royal Institution, so where Faraday gave his lectures on electromagnetism and so forth. I was just giving this talk on quantum mechanics last night, and I realized every other name that I mentioned had been doing work a few miles away, one place or the other, from Rutherford to Dirac and so forth.
Yeah, you walk into Westminster Abbey and you see, like, Sir Isaac Newton buried there, and it's like, it's heavy.
Yeah.
Heavy-duty stuff.
It's right next to Stephen Hawking, right? Yeah.
Right, yeah. He's just newly there as well. I kind of walked over his, I don't know, is that his grave there? Or maybe I don't know if he's buried there, but he's got a,
right, I think it's a memorial of some
memorial
sort.
there. So, all right, so it feels good to be here. You feel kind of
Very
at home.
I really enjoy it, yeah.
Okay, gotcha.
I eat very well when I'm in London. Actually.
Yeah, maybe you should break the myths about London food. It's because we've had a bad rap here about food in London.
The bad rap is not just invented out of whole cloth. I think that every city has a different food culture, and London. It's very possible to get bad food in London. I think what people don't know is it's just as possible to get good food if you just like put a little bit of effort into it. And I mean, either world-class fine dining is absolutely available here, but I just love all the different ethnic restaurants that do things in very creative ways. We went to a place called Scully's the other night, which is, it refuses to say where it's from, but it's clearly a lot of North African influence, lamb tagine kind of things, roasted carrots with so many spices in them that I couldn't even begin to name them.
Yeah, the cultural cuisine is off the hook.
Yeah.
And like Indian food is the Mexican food of Britain, Right. So in America has great Mexican food. We have great Indian food.
I made the mistake of ordering chicken quesadillas, and like, why am I going from Los Angeles to London and ordering chicken quesadillas? That was not the best choice I could have made.
How'd they compare?
They were fine, but I'm like, why did I choose this? Get the chicken tikka masala.
Yeah, no, but you're right. It's easy to find bad food and also easy to find really amazing world-class fine dining and even just a curry. I mean, I've had Indian people that tell me that curries are better here than in India. So, so long live London. Look, I want to talk about all sorts of stuff. I want to talk about quantum physics and quantum mechanics and a lot of stuff in your book. But I want to maybe go down a little bit of a memory lane because, believe it or not, Sean, I used to be a scientist back in my day.
Totally believe it.
I won the San Diego County Science Fair. I went to the California State Science Fair. I used to build these little like homemade cathode ray tubes, and that was my identity when I was a kid.
Right.
I was like a science geek. I later went to MIT, got a degree in mechanical engineering, and graduated the same year I think you got your PhD from Harvard. I didn't realize you then came down and spent some time at MIT.
Of course.
I have such fond memories of being there and of learning the science and being around like such a great institution with all these big minds. Again, walking through the infinite corridor at MIT, which is this long corridor. Everything has geeky names at MIT, since everyone is a geek a little bit. But there's like all of these epic historical people that went there as well.
Yeah.
What do you remember from your time in Boston?
My first experience was I was a grad student at Harvard, and I found out that you can cross-register for courses at MIT for free. You can just take courses at MIT if you're a student at Harvard. So everyone knew, like there was scuttlebutt in the physics departments, which courses were better at MIT and which were better at Harvard. Everyone from MIT came to Harvard to take quantum field theory, but everyone from Harvard went to MIT to take general relativity, which was a subject I was very interested in.
Okay.
So I registered for the course, and I'm on the phone. It was before the internet was really very popular, so you had to like call, and they said, yeah, it's in building 6130 or something like that. And I said, yes, but what's the name of the building? And they had to explain to me that 6 was the name of the building. We don't give our buildings names, it's just numbers. The subjects are all numbers, and I never learned the numbers despite spending many years at MIT. I just could not keep the numbers straight in my head.
You're right. I never thought about it, but yeah, building 6, building 7, building 10, and you don't have a major, your course 2 is mechanical engineering,
like,
course 1 is civil engineering. You get the feeling
that if they could reduce everything to numbers, they'd be much happier.
What are you trying to say,
eliminate
Sean?
Words.
Yeah. No, you're right. That's like the ethos of the place. Yeah. And the courses
despite having a world-famous linguistics department with Noam Chomsky, right?
Right. Yeah, no, they do have these weird pockets of surprise there. And so were they better at certain, Would you say the MIT courses were better at things that were more like lab-oriented and research-oriented stuff, and Harvard was better at the theory, maybe? Or does it depend on the professor?
Yeah, at the graduate level, it just depends on the professor, right?
Okay.
I mean, for undergraduates, there's an experience. I think, undergraduate education is really, I think, where you become who you are in some sense, right?
Yeah.
And going to MIT, you're going to become a different person, or you're going to want to be there as a different person than going to Harvard or Penn State or UCLA or whatever, or Caltech for that matter. But once you're in grad school, they're all kind of the same because the grad students come from all these different undergraduate institutions, and it becomes a little bit more mixed. So it was just who's the good professor, yeah. And MIT at the time had really good, and still today has really good teachers of upper level physics courses. So it was a great opportunity to go there.
And how would you say the cultures are different between Harvard and MIT? Because you know.
They're very different, and saying that they're very different matters because, honestly, I've been to a lot of universities in a lot of different contexts, and most universities are not that different. The United States has hundreds and hundreds of universities, and most of them are pretty much the same.
Okay.
And Harvard and MIT, and also Caltech, where I am now, are a few of the ones that are really unique. And at MIT, the feeling I always got was that everyone works harder than everyone else. This is their self-image. They keep telling themselves how hard they work, right? And a lot of them are entrepreneurial, right? People starting businesses and things like that. At Caltech, the students also work hard, but no one's going to start a business. They're going to become a professor of something someday.
Right.
And at Harvard, it was neither one of those. It's just we rule the world. We're the ruling class. We are the sons and daughters of princes and sultans and presidents and senators, and we'll be fine. And there's a few quirky artist types in there, great lacrosse players or whatever, but it was high-achieving people or high-born people and a whole bunch of things who were pretty convinced that they were the world's elite.
Right.
And it was a little more relaxed for that reason than MIT ever was.
And that's like a powerful thing to install to a young person, that you are expected and you will become a leader of this world in a corporate sense or a political sense.
Our graduation speaker was Al Gore because his daughter was going there, and he had gone there, and Natalie Portman was going there at the time, and you just got used to that kind of thing. And I was not used to that kind of thing, but again, grad school is a little bit different. You're in this research-oriented, very focused world. I think it can be very good. If you go to a place like Harvard or MIT, because they are unique, they're not for everybody, but for the right people, they're amazing. The opportunities are just absolutely incredible.
Yeah, no, I think you made a really good assessment there. When I was at MIT, I lived in a fraternity with 50 guys, and I don't ever recall having a conversation about what family they came from or how much money they had or power. All we tried to worry about was who could get a better grade, if we could even make it through this course without dying, how hard we needed to study. And it was a real, I felt like I was in a pressure cooker there. And I liked that because, you knew what you had to do. And if you did it, then you would be successful.
My impression is you wouldn't have a conversation about that at Harvard either because it was just taken for granted, right? But you would, I think that, the difference is the idea of let's start a magazine. That's like the kind of thing that we do, right? And that was never part of my upbringing. I came from a long line of steelworkers and secretaries, and so just the idea that we will affect the world in some important way is quite impressive in the sense that it gives you a little bit of a mission, a purpose, if that's what you want.
Yeah, no, very much so. And just to finish out our appraisal of the
reminiscing
of the U.S. college system, Caltech, which is where my father went to school. He graduated in 64 undergraduate, 65 with a master's degree in EE, and he came from a farm in Arizona. So for him, it was quite a culture shock to be there. I went there with him when I was 18 years old to look at the campus. Now, Caltech is probably closer to MIT than any other school as far as they're both very high-level technical institutions, but they're also very different. How would you describe Caltech to people?
Yeah, it is. I would have thought that they were the same or very similar, just East Coast, West Coast, but they're very different. MIT is much bigger, much more diverse. MIT has world-class departments in economics and linguistics and even English. Caltech has one department of humanities and social sciences, and there is, an economist and a couple philosophers and a couple historians, but guess what? They're doing philosophy of science, history of science. The English courses are in science fiction. It's extremely focused on science, and it's much smaller, and it's very top-heavy. There's very few students. The graduating class is like 400 people every year,
right.
And the number of professors is huge. And you don't, almost every university, there's always this thing where if you're a professor, you know when September has come along and the students have arrived and the campus comes to life. And at Caltech is just no different from day to day because there's just as many people there doing their work every day of the year.
Yeah, I feel like there were smarter people at Caltech when I walked around. When my dad took me to Caltech, I walked around and I saw like a bunch of really intensely smart dudes. And then I went to Boston and I went to a fraternity and the guys got me drunk the night before. And then I went and saw somebody crooning in the subway and I fell in love with the city and I was like, I'm gonna go here.
Yeah. So, I mean, well, Boston is a wonderful environment too, especially, you know, both MIT and Harvard, I think, you have the feeling that you're intellectually the center of the world when you're in Cambridge, Massachusetts as a young scholar, one way or the other. You know, there are people coming in, and, you know, there are people who are already there, and it's just exhilarating.
Yeah, and there's like 40 or 50 colleges in the greater Boston area.
So many students,
it's just full of this, like you said, you feel like you're in the center of like education.
And because Caltech is so small, and it doesn't make a huge effort to become integrated into the community, there's no feeling in Pasadena that you're in a college town in the same way that there would be in Cambridge or Boston.
Yeah, that's true. All right, good. So if anyone was thinking about any of those institutions, there you go.
They're all great, but they are different. Know that they're different and find the one that works for you, would be my advice. Yeah.
Totally agree. The last thing you would want is to, want a degree in politics from Harvard and go to MIT. I mean, you would want to run away from that place and vice versa.
Yeah, exactly.
So yeah, definitely tour the college, get to know who's there. Do you ever look in the mirror and say, wow, this is weird? I'm an expert in quantum physics and I'm on the Colbert Report. You know, that I'm being asked to go on these massive television channels and talk about stuff that maybe when you were younger thought was very esoteric and only would be understood by so many. Are you surprised by how many people actually care about this stuff?
I'm kind of not surprised. I think that there's a bit of a reputation, or at least a cliche or something like that, when you mention physics, or especially the more out there areas of quantum physics or cosmology, to sort of act intimidated and afraid of it. But I think that once you get past that, there's a lot of people who genuinely have a real interest in this stuff. And when we scientists make the effort to make it a little bit more accessible, a little bit more understandable, a little bit more human and relatable, there's a huge positive reaction to that. It is funny though, so I'll admit, like I was on the Colbert Report, and that's the one thing I've done in my life that will always get mentioned when I get introduced. So it's like my best accomplishment so far. But you know, in the US, for American listeners here, he was on Comedy Central, cable channel. Now he's moved to CBS, a network channel, and the show has changed, and I don't appear on the show anymore. And part of that is when he was on cable, he could sit down with a person for 5 minutes and have a conversation with anybody, with a writer, a historian, philosopher, scientist. And now that he's on network TV and it's kind of broader, there has to be kind of a spectacle. So there's still scientists appearing, but they're doing demonstrations and blowing things up and so forth, which is not my gig, right? I'm going to sit down and talk about the nature of reality, and they're like, yeah, we kind of don't do that anymore. So there's still, a lot of people who are in the TV world have that intimidation about science that I think is kind of a shame.
Yeah, well, it's still kind of a shame that TV is about the 5 minute, the spectacle, the pow, the boom. Whereas I know you have a podcast, and what we do here is long form, and people can get as much as they want, and they love it. And you've been on things like the Joe Rogan Experience, where people will listen to you for 3 hours, and it's an amazing thing to have this kind of media on tap that people can have.
And it's not for everybody. Like my podcast is for a general audience. It's called Mindscape, and it's for people who are not scientists or whatever. But it is for people who are sufficiently interested to listen to a 1 or 2 hour conversation with an expert trying to get into the details of what they're doing. So no prerequisites, no knowledge assumed, but the inquisitiveness, the curiosity is definitely assumed. And it's just been great to feel that people really respond to it.
Yeah, I love it. All right, how do we get into this? Because I'm just now picturing my aunt who's in Denver, who's in her 70s. And I'm just thinking, okay, Marianne, how do we convince her that maybe learning about quantum is important? And how do you first start having these conversations?
Yeah, there's a lot of it's just like picking a university. Different people will get into it for different reasons, right? I mean, there are people who just care about the fact that quantum mechanics is central to modern technology. Quantum mechanics, just to back up a little bit, It is the way the world works. It's the replacement for classical mechanics that Isaac Newton came up with in the 1600s. And after Newton came up with classical mechanics, that's what you were tortured with as an undergraduate, with pulleys and levers and inclined planes, right?
Yes, the basic physics we kind of all learned in high school, which seemed really simple. You've got the gravity, you've got, like you said, the this does the this, and then everything plugs in perfectly.
That's right. And it was clean, crisp, literally the clockwork universe, right? That was Newtonian mechanics. And it was so good and so compelling that people thought, that's how the world works. And it was not really, Newtonian mechanics is not a specific theory, it's a paradigm, it's a way of doing physics. And it applies whether you're talking about particles or electricity and magnetism, the planets or whatever, the ocean currents. And then in the early 20th century, we began to realize, yeah, it doesn't quite work that way.
All the time.
It doesn't, yeah, it's fundamentally not just you take Newtonian mechanics and tweak it a little bit. Fundamentally, you throw it out and you replace it with something totally different. And that's what quantum mechanics asks us to do. And the central idea that makes quantum mechanics different is that in Newtonian mechanics, you have okay, there's a planet going around the sun. You give me where the planet is, how fast it's moving, where the sun is, and I can tell you what it's going to do. And literally people do this on computers, right? They simulate the future of the solar system.
Right, and Kepler used to do that in the back
Kepler,
in the day.
Galileo, Newton,
all those guys used to watch
Hooke,
it.
yes.
And that was all based on Newtonian
Well, Kepler was pre-Newton. Kepler helped
pre-Newton.
inspire Newton to figure these things out. Kepler figured out that planets move in ellipses, not in perfect circles.
Right.
And then Newton said, oh yes, if the law of gravity is the inverse square law, I can predict that planets move on ellipses. So that was his great triumph.
Right.
But then the difference is in quantum mechanics, if you talk about an electron, for example, okay? In fact, the electron, there's the classic picture of the atom that we've all seen, with a little nucleus at the middle, and the electrons are what look like little planets, almost just like a little solar system, right?
Right.
So that's a very comforting picture. We've seen pictures of the solar system. Here's the atom. They look very similar.
Perfect circle. It's all happy and perfect.
That's right. And as it turns out, that picture of the atom is complete BS. It's not what atoms really look like. And you know that because an electron zooming around an atom would give off light. All of the light that we see here in this room is from electrons jiggling up and down, emitting radiation. And therefore, the electron would spiral into the middle. It would lose energy. It's not a stable configuration. So the answer as to why electrons stay in their atoms is that they're not little particles moving on orbits. They're waves. They're a cloud that is spread out and sort of settles into some minimum energy configuration. So this is, we're talking about now 1910s. People figured this out. If you think about electrons as little clouds, everything's okay.
Right.
The problem is, when you look at an electron, when you shoot an electron through a detector, you don't see a big cloud spreading out. You see a particle moving along a line, right? And believe it or not, the thing that physicists convinced themselves of in the 1920s was, here's how to describe reality. When you're not looking at it, the electron is a wave. And then when you look at it, it's a particle. And people like Einstein said, oh, come on. Even if that's true, that can't be the final answer. Let's try to do better. But people like Niels Bohr and his friends said, no, it works. Let's move on. Okay.
And there was like a name for that theory that when you
the Copenhagen interpretation of quantum mechanics.
And when you observe something, it fundamentally changes it. Which people understand that concept, but like you said, it feels like it's a
what do you mean?
together.
So the question is what counts as observing, right? Does it have to be a person?
Yeah.
Could it be a cat? As Schrödinger famously wondered. Could it be a video camera? What if I don't look at it very closely? Does that count?
What if you just look at it?
And the answer is, you're not supposed to ask those questions. The answer is, quantum mechanics seems to, in the way that we teach it to our students at MIT or Caltech, the act of observation is a primitive, fundamental notion. Now, that's kind of silly and absurd and shouldn't be the final answer. So people like me are trying to do better than that. But that's the mystery. That's the reason why quantum mechanics is difficult to understand, because it involves words like measurement and observation that are just not very well defined.
Okay. And I remember being taught that it's a particle and it's a wave and it depends on the time. And growing up in a Newtonian world as a kid and living in this reality, whatever we want to call this, that just doesn't make any sense. You
Yeah.
really, I mean, now it feels like you're in a religion class, right? A little faith.
Well, it's very interesting because psychologically, the reason why it's hard for physicists to really come to terms with quantum mechanics is everything in our scientific intuition says the world is what it looks like. We look at the world and we see it. And the whole point of quantum mechanics is that we look at the world and what we see is something a little bit different than what the world really is. Right. And so that's very hard to reconcile. And we say, you know, is it that the true reality is something very, very different and we have to give up on the idea that we see the world directly? Or is this set of words about waves and clouds that we use to describe reality just a crutch and what we see really is the reality? And so that's a debate that's still ongoing.
Okay. Now you're mentioning 1910, 1920 when this stuff starts to get funny. Is that because of Einstein? Is it because also we were able to start to measure things a little bit closer and we started having access to nucleuses and soon to be atomic bombs?
Yeah, very much. You know, almost all the great revolutions in physics are driven by better data, one way or the other, right? Better experiments. And there were two ideas that really bugged people in the early days of the 20th century. One was what's called black body radiation. So if you just take an object and you heat it up to some temperature, there's a wonderful feature that every object, no matter what color it is, no matter what shape it is, no matter what material it's made of, if it's at a constant temperature, like you put it in an oven and heat it up, it glows in exactly the same way, every single object. And there's a very, very clear spectrum that it has, a certain amount of red light, a certain amount of blue light, etc. So you can try to predict that, theoretically, using the tools that you had in the year 1900, and you get it wildly wrong. So Max Planck comes along and he says, well, maybe when the light is emitted, even though it's light, even though our friends here in England, like Maxwell and Faraday, told us that light is a wave in the electromagnetic field, maybe when it's emitted, even though it's a wave, it's emitted in little chunks, right? Like a little bit here, a little bit there, rather than smoothly and continuously. And with that out of the blue idea, he fit the data perfectly. But everyone's like, well, what does that mean? And it was Einstein who actually said, you know, the difference is the following. Planck said the equivalent of, I have a coffee maker that gives me coffee in 1 cup increments all the time. Okay, I push the button, I get 1 cup of coffee. And that's one little photon, one little particle of energy. And Einstein came along and says, coffee only exists in 1 cup increments. So he said that it's not just that light is emitted by a hot object, 1 particle at a time, but light is particles, is what he said, which is sort of completely incompatible with everything we thought we had figured out in the 1800s. So that's the first sort of particle versus wave-like thing. And then this thing with the atoms, the electrons in the atoms, people were like, why don't electrons fall in? And Louis de Broglie, a French physicist, said, well, if Einstein says waves can be like particles, maybe the particles, the electrons, can be like waves.
Right.
And then that also worked, but you know, it was clearly a sign that something was moving toward the same direction, but reconciling everything took more years than that, yeah.
Okay. We keep mentioning Einstein. Tell us about Einstein. I mean, you know, everyone knows the images and everyone knows the myth, but what was he really, and what did he add, and what did he question?
So Einstein was a smart cookie, as it turns out. I think, if anything, this is almost going to sound silly, he's underrated.
Okay.
And he did win the Person of the Century and the whole bit. But we have this image of Einstein, you know, in the early 20th century with relativity. You know, he came up with space-time, and then space-time is curved, and that's gravity, which eventually led other people to things like black holes and the Big Bang, and it's a big deal. And one of the fundamental things about gravity and general relativity is that it's more or less a one-man show. Einstein was the only guy who was really pushing on that, and he figured it out. Whereas with quantum mechanics, it took 20 people, you know, years to really get this right, arguing with each other back and forth all the time. There's many different contributions from many different people, so you can't point to one person and give them the credit for quantum mechanics in the same way that you can give Einstein the credit for general relativity. So just for that reason alone, he deserves a lot of credit, and he gets it. But then there's this story that you will hear that Einstein couldn't quite cope with quantum mechanics, right? So by the time quantum mechanics is put into its final form, it's around 1927. And there's this image of Einstein as an old man who can't quite keep up with the times. Now, he was like 48 years old. so I don't want to be told that he's an old man at the time. But also, that image is wrong because Einstein understood quantum mechanics better than anybody, including the people who are given credit for inventing it. The difference is that he just wasn't willing to accept that it was done, that it was, he wrote a famous paper, can the quantum mechanical description of reality be considered complete? He thought there was more to the story and we should keep looking. And I think he was right about that. I think that the stories that we were telling ourselves in the 1920s are woefully incomplete. So I do think that, he had some ideas near the end of his life that turned out not to work, but we've all had ideas that turned out not to work. I think that his judgment was really, really good on these issues.
Do you ever wonder how a guy in Switzerland on his own, without laboratories, came up with this? Or is it because it was a complete paradigm shift in a way of looking at things? I mean, do you ever think about that?
Well, Einstein had, in 1905, he had what is called his miracle year, where he has, 4 different papers published in the same journal, any one of which should have won the Nobel Prize. And we do think about that, how in the world that happened. And he was not even a professor at the time. He was a patent clerk, right? And maybe you can say, well, being the patent clerk gave him more free time because, it was not a very difficult job. It was enough to pay the rent, basically. But no, somehow he had this way of figuring out exactly which parts of the phenomena were relevant and which parts were irrelevant, which parts you could throw away and which parts you could keep. In fact, his first major contribution to relativity, there's special relativity that is all the business about the speed of light being constant and the clocks and so forth. That's 1905, and then it was 10 years later, 1915, that he says, well, maybe this space-time is curved and you get gravity. Special relativity was not just Einstein. He was building on things that other people did. In fact, his major contribution was to say, we can simplify everything. There was this idea, there was the ether, this invisible field that filled all of space, right, and light was propagating through the ether. And it took Einstein just to say, if you remove the word ether here everywhere, and you just say light propagates through empty space, you get all of the phenomena correctly described in much simpler terms. All you have to do is give up on the idea that there's an absolute space and an absolute time, which is a lot to give up on. And he was just a genius at giving up on the right things.
Wow, and that probably is the history of great movements in human technology and understanding. People who know what to look at, and then people that can also walk away from previous assumptions.
It's fascinating to me because there's no one right way to be a great physicist. There are different physicists who have very different styles. Just at Caltech, where I am, in the 1960s, we had both Richard Feynman and Murray Gell-Mann, who were the best theoretical physicists in the world at the time, but very, very different styles. And styles come along with different predispositions, different feelings, different intuitions about how nature is going to work. And the dirty little secret of theoretical physics is that it's not an algorithm. There's not a way to go from the data to the correct story. You're going to guess. You're going to say, well, maybe it's this way, maybe it's that way. Different people will make different guesses, and in different historical circumstances, different guesses are going to turn out right. Like Einstein in 1905 made all the right guesses. His intuition was spot on again and again. And then when it came to the 1930s and 40s, when he was trying to unify gravity with electromagnetism, all of his guesses were wrong. And he didn't become dumber. It was just a different time, and different problems were ripe for being solved at that time.
Okay. And yeah, you mentioned Richard Feynman. I mean, he's kind of a legend at MIT and Caltech. My dad actually took that freshman physics class from him, I think in 61 or something.
Yeah, I have Richard Feynman's old desk.
Really?
At Caltech, yes.
Oh my gosh. Gotta make sure that's not stolen from you. That's like
There's a little sign on it at the bottom that says Feynman's desk.
Okay.
So
he's quite a legend over there. But again, a really forceful personality. I mean, personalities matter, because a personality can drive forward an idea, a concept. I mean, look at Stephen Hawking, look at Feynman, look at Einstein.
Yeah.
It's strange that in a field that's about the numbers and about the theory, how a personality can change things.
Absolutely, and no better example than quantum mechanics, really, and Niels Bohr, who was sort of Einstein's counterpart on the other side. Bohr, clearly a genius, did absolutely central work in establishing quantum mechanics. He was the one who figured out, that electrons come in certain orbits and not other orbits, which was a crucial step. But and he was a very different personality than Einstein, much more charismatic, gregarious, social. He worked with people. He founded a school and an institute. He had acolytes and followers. Einstein, much more of a loner, just kind of wanted to do his own thing, be left alone. And that was crucially important to winning the marketing battle when it came to the interpretation of quantum mechanics. Bohr said, like, okay, we're basically done. Everything is fine. Einstein and Schrödinger and other huge names said, no, we're not done. What are you talking about? And Bohr won, clearly, decisively. Like, he was the one the physics community went along with. And so it does matter. And I think that that's an example where it was a mistake. You know, like sometimes force of personality and charisma and persuasiveness help people accept difficult ideas. Sometimes they kind of hold them back from tackling different ideas.
Right. And I think I saw somewhere you assert that, like, since 1927, we haven't been as curious as we used to be about physics. Can you explain that?
Well, about the foundations of quantum mechanics in particular. So we had this idea, you know, put together by the late 1920s. It was all, there was a system in place, and that system had this statement that, you know, electrons or other quantum systems are waves when you're not looking at them, and they look like particles when you are. So the question is that a way station? Is that a partial solution to the correct eventual solution, or is that just it? And the physics community decided that's it. And we're not going to ask questions about what's really going on underneath. We're just not going to worry about that. If you write a paper about the foundations of quantum mechanics, the journals will reject it. Your colleagues will look at you as if, oh, it's too bad you no longer do real serious work anymore. There's example after example of people either, you know, being told not to do this, or people who already had established careers hiding from their colleagues the fact that they were working on the foundations of quantum mechanics. And I think it's finally changing. I think that, you know, both we're kind of stuck in fundamental physics in certain ways right now, but also for, again, technological advances have brought us to the point where we're building quantum computers, and the need to truly understand quantum mechanics is front and center, so people are beginning to take that problem a little bit more seriously.
It only took us 100 years.
Only took 90 years, let's be fair, yeah.
That's strange, but also from what I understand about academia is that it is kind of these weird, it's a weird club in that sense, where you can't bring this up and you have to do this and to this appointment. I mean, in a weird way, it's the opposite of the free market.
Well, there is a free market there, but it's a free market of ideas, and you have to persuade people that your idea is worth following. And just like the free market, it's not that you're just, you know, doing an experiment and collecting data. You're trying to affect people's opinions, right? You're trying to, if you're in the free market, you want people to buy your product, and there's something called advertising, and you know, there's supply and demand, but you can try to generate the demand. It's not just there as an objective fact. It's exactly the same thing in academia. You have an idea, your idea may or may not be right, but you certainly have to sell your idea. You certainly have to convince people that your idea is interesting. And ideally, the best ideas win, and I think in the long term, the best ideas win, but moment to moment, a good idea can really struggle.
Right, right. Talk to me about the Hadrian Collider, because I think that's something that everyone watches, they see, and I think most people would say, you know, they're obviously looking into some quantum aspects and some atomic level stuff. What have we learned from the collider, and what have we not learned?
Well, I think this is a great thing to talk about because it shows the difference between what particle physics has become really, really good at and what it's choosing to ignore. So things like what the Large Hadron Collider in Geneva does. This is a giant, you know, 25-mile around ring under the ground, where there's these tubes that are emptied out and you shoot protons around them very, very close to the speed of light, 99.999999% speed of light, and they smash into each other. And you ask what comes out, okay? And one of the things that came out was the Higgs boson, discovered in 2012. And both doing those experiments and making the predictions, theoretically, for what's going to be seen by those experiments, that's where physicists are really, really good. I mean, the Large Hadron Collider was literally the most complicated machine ever built by human beings. And the predictions of these particles were made in the 1960s, and then it was seen in 2012. So the predictions are just made by theoretical physicists like Peter Higgs, Francois Englert, Robert Brout, and based on trying to come up with a theory that made sense. You know, you knew some basic features of the world and you knew the math. And just on the basis of that, they were able to see decades into the future and say, if you do the right thing, you'll see a little particle being created. That's just exquisite and beautiful and a real triumph of both human beings trying to understand the world and of the power of physics to get the world right. Just like Einstein in 1915 coming up with general relativity, and then we discover gravitational waves from black holes in 2016. On the other hand, you don't need to understand much about the foundations of quantum mechanics to do the Large Hadron Collider. All you need to know is you smash particles together, there's a certain probability that when you observe what comes out in your detector, you're going to see this particle or some other particle. If you say, yes, but what do you mean observe and measure and all those sort of philosophical sounding questions, nobody knows or cares who works at the Large Hadron Collider. That is not their deal. They want to predict what you will see. They do not want to ask what's really going on at that moment when the measurement is being made.
So in a weird way, it's not that advanced, or not.
Well, it's advanced in one direction,
Right.
but not the other,
Okay.
right? And so we're choosing to be really, really good at one kind of thing, which is very practical. Like one of the reasons, there's many reasons, but one of the reasons why the focus of physics shifted in this way was the center of physics moved from Europe to the United States, right? Like all of the great founders of quantum mechanics were European, one way or the other. But then the next generation of real geniuses like Feynman, like Gell-Mann and others were mostly American. And the Americans, bless their hearts, but they have a much more practical attitude. They're like, what can I do with this? What can I build with it? What can I make with it? Right. Or at least, even if you're a physicist, what can I observe? What can I see? Right? What experiment can I do? People like Einstein and Bohr were deeply immersed in traditions of philosophy and humanistic inquiry, and people like Richard Feynman were not. They didn't want to hear about that stuff. Right. And so, there's this joke that the motto became "shut up and calculate." And that's not really the motto, but it's a pretty good, summary of what the attitude became.
Okay. All right. And now that's why CERN is in Europe, you think? It's more theoretical.
Well, we had, in the United States, we had Fermilab, which was sort of the competitor to CERN for a very long time. And it's this weird thing where certain kinds of particles were discovered in the United States and certain kinds were discovered in Europe. So Fermilab discovered the top quark and a lot of other very important particles, and they were rivals. But the United States has more or less given up on this chase. We had this proposal to build the superconducting super collider in the 1990s, and it fell victim to the budget battles. And Bill Clinton, who was president, did not really support. He wanted it to be built, but he didn't try, right? And so Congress just canceled it. And it would have been a higher energy machine than the Large Hadron Collider in Europe. And Europe, has gotten their act together a lot better than the United States has. They have, which is amazing because they're multiple countries, right? Yeah. They have to agree. And so it's both good and bad that there are multiple countries and they have to agree. Like on the one hand, you might worry that there's a lot more failure points. Like any one country can just say, yeah, I don't want to do that anymore. Well, on the other hand, there is a spirit of cooperation and working together. And, okay, well, if France is donating money, then we should also donate money, that kind of thing. Whereas the United States, every 4 years, has a presidential election and they just throw out everything that was done 4 years previously.
Yeah, no, for sure. Now, look, as a common person, how is quantum physics going to be affecting my daily life? And what do I need to know? I mean, these days we're carrying around things that use it all the time, I guess the sun itself, but what are some things that we should know and maybe even prepare us for the future, 10, 20, 30, 40, 50 years from now, when it might make more of a difference in our life?
So there's the answer that I kind of am tempted to give, and then the better answer that I should give. The answer I'm tempted to give is we're trying to do this just because we want to understand the fundamental nature of reality. It's not going to make you a better iPad, a better cure for cancer, a better TV set. The technological implications of quantum mechanics, we can do. We can do those already. The kinds of questions that I want to know about, is there multiple worlds out there? What happened at the Big Bang? These have no direct implications on how we will live our day-to-day lives. I think that's a fair and true answer. But the other thing is, advances in understanding do come along with advances in technology, even if they're unanticipated. You know, the idea that you can build a quantum computer, for example, which Feynman was one of the first people to point out. This might be crucially important to future technology. You're not going to probably have a quantum smartphone or anything like that, but if quantum computers can break codes or simulate complex physical systems that couldn't otherwise be simulated, that might be revolutionary for computing power.
And how does a quantum computer work differently than what we currently have? Just if you had to explain that.
There's a couple things going on. One is if you just have a bit, right? A classical computer pushes around bits, ones and zeros. Right. Quantum mechanics says rather than a bit, you have a qubit, very clever name for a quantum bit, okay? But what it means is instead of a 1 or a 0, you have a combination of 1 and 0. You can be almost all 1, very little 0, or vice versa, or any combination thereof. So you, in principle, every single quantum bit contains an infinite amount of information because it's some number between 0 and 1, right?
To continue watching the rest of the episode for free, visit our website londonreal.tv or click the link in the description below.